Okay. All right. Let me change this text to a little bigger because it may not be visible to many people. All right. Okay. Cool. So, all right. Everybody able to hear me clearly? And all right. Good. Good. So, all right. So before we start our discussion, let me rephrase where we are standing as of now. So we started with what is big data. Okay. We talked about we talked about the situations that when the data starts growing big, the usual tools such as file systems, databases, and other tools cannot suffice. And that's where we realize that we need new generation of tools. And luckily, Hadoop is one of those tools which provide comprehensive solutions to various problems where the data size is big, fast, and complex. All right. So that's a quick. And why do we want to churn big data? Because bigger the data, better the analytics. Bigger the data, better are the results. And bigger the data, better are your better are your what do you say predictions. So in that's probably the one of the reasons why we are trying to do the big data analysis. Earlier, we used to do like sampling and then take do the analysis, but now data is available and we are able to churn the huge data. When we say huge data, billions of record, millions of records. So that's big data. So there are many use cases, and to tackle big data, there are many solutions. Hadoop is one of those. And in Hadoop, the first thing is a file system. That's probably the most important thing when it comes to anything. Even in the normal computing, the file system is very important. Okay, file system is very important, and here we are provided with HDFS, Hadoop Distributed File System, which basically runs on many computers. One of them is name node, others are data nodes. Name node just has the information about the data, while the data nodes contain the information actual data. And this data, each of these files, and the way we store in data in HDFS in the form of folder structure files, so we can upload files and download files from HDFS. Even if the file is of terabyte size, HDFS is comfortable. And if at point of time, if HDFS is not sufficing, so since HDFS utilizes many computers to serve the storage, okay, therefore, if you have 10 computers, so 10 computers total disk size is what counts as HDFS. So if you have 10 data node and you have, I'll just talk about this special case. So if you have 10 data nodes, okay, if you have ten data nodes, meaning 10 nodes which will contain the data, while name node will be a single one. Okay, name node will just be the gateway to find out the information about data. And these 10 data node, let's say they contain 100 GB each, right? Now, now since there are 10 nodes, so how much is the total disk storage? So on an average, we devote around 75% of each of this machine. Now, can somebody help me with the numbers? So 0.75 percent of 100 GB on each into 10 nodes. That is how much? Yes, 750. That's right. Now, this 750 GB is the total storage. Now, imagine that since HDFS, so we talked about two quick things. One, it contains one name node, multiple data nodes. And in our case, 10 data nodes are there right now, just as an example for this case. And there are one name node. So data node is 100 GB each. And when a file is given, the file is sliced into small portions and distributed on these data nodes. And these data nodes contain the replication of every file's block, because every file is sliced into small blocks of each of 128 MB size, and this each block is replicated. That means that if you are storing 1 GB, it's going to take 3 GB of storage. So effective storage you get is around 250 GB, right? The effective storage you will get is around 250 GB, unless you change the replication factor to lower than this. All right. So in HDFS is built of name node and data nodes. Name node stores information about where is data, and data nodes store the actual data. The objective of the whole HDFS exercise is to store huge data and cater to many users. And how does HDFS do it? Utilizing many computers. And when you store data in HDFS, HDFS basically splits the data. The driver, HDFS driver, using which you will talk to HDFS, will split the data into blocks, and those blocks are going to be allocated on these data nodes. And each of the block, okay, so each of the block is going to be copied to other block as well, and this is called replication. And by default the replication is thrice, meaning replication factor is equal to 3. You can change it to lower or above. All right, so that's a quick you know that's a quick recap of HDFS and big data. All right. Now, there are a few questions I need to answer. So please feel free to ask questions because, okay, because there is no hurry. And even though questions might be, concept might be clear to you, there would be somewhere the doubt would be there. And those doubts would arise if you think about it a little more or try to answer other people's question who are asking. Yeah. Okay, so there is two, three questions, and let me answer them one by one. Okay, right. All right, this is better. Okay, now this is very good. Let me just store these notes. Okay, and today is 11 June. All right. So there is one question from I think Ajay. Can you please elaborate more on when is write treated as success in HDFS and when it writes to the edit logs? Okay. All right. Now, okay. So here we go. So, all right. So who has this clarity on this question? Okay. Anybody in the class? Yes. Yes. So what happens is, so the user goes to first name node. Okay, name node, and name node marks. Okay, so when user goes to name node, it creates a temporary marker marker for the file. Let's say you want to change a file, you go to name node saying, hey, I want to store this file, and my file is going to be this big, and can you suggest what to do? Name node will reply to you saying, why don't you go to these three data nodes, and this is your block ID, and go to the data nodes and start storing there. Just communicate this information to data node, and data node will accept your request. Now, user would go to user. I mean, when I say user, we are talking about the HDFS driver. Driver is like somebody who, a driver is basically the command that you use for talking to Hadoop. And the way user goes, so all of this is happening behind the scenes for you. Okay, so uh, so uh, uh, yeah, so user, the SDFS driver goes to data nodes. Okay, and once that data nodes and writes successfully. Okay, and then user or HDFS driver again, user and HDFS driver again goes to name node to confirm. So this is the general mechanism. Now, next question is, okay, next question is, can you please, when the write is treated as success in, now, once this gets committed, okay, once this get committed, now another process start. So name node queues the write to the disk. Okay, what does it mean by queues write to the disk? So name node it contains the whole information about the file system, which is metadata, as in information comprised of what kind of folder structure is there, what are the files in each folder, and so on. And each of these files, what is the name of the file, and each of the file is located on which data nodes and what are the block numbers. So this whole thing is a metadata. Now, in a decent or a practical folder structure, on a realistic folder structure, this folder structure is going to be fairly huge. Okay, so it's going to consume a decent amount of memory. Therefore, name nodes are generally high-end servers as opposed to the general philosophy. And name node keeps this data in memory so that it can cater to the user request really fast. Otherwise, since name node being the single entity, the whole system will become extremely slow. So name node keeps the whole metadata in the memory, and whenever there is a change, like you are writing a file, you are appending a file, so modification and creation are almost same thing in case of name node, because name node so HDFS is more or less is append only file system. Okay, so meaning if you append to existing file, HDFS is happy with it. But if you try to modify a file, it's going to rewrite almost the whole file again on many. A modification of a file is equivalent to writing a fresh file, just like your normal file systems. Now, coming back to the point which you are trying to make. So this metadata which name node is storing in the memory, if you are writing to a file, creating or updating, creating or appending. So this metadata needs to be updated, right? And if this metadata needs to be updated, it is not possible for name node to keep on purging the whole metadata again, saving this full metadata into a file system is a very big headache, right? Because the whole file system has to go to the file system. And if it starts doing that on every change, every time the user saves, if it starts saving the metadata into the disk, what would happen is that it will become very slow. Writing a single file will take a lot of time, right? So what to do in these scenarios? So exactly the way we maintain our accounts. How do we maintain an account? Whenever there are quick transactions, every accountant or every um, finance person maintains the log of various transactions, that this transaction was done from this account to this account. That's a rough notebook. Okay, these are like keeping the information in a temporary location, and periodically, every month end or every something like that, accountants transfer the data from journal, these called journal, into ledger. Similarly, NameNode transmits. So NameNode keeps for every change you do, it makes something called edit logs. These are the logs saying this file got modified from here to there. This got modified from here to there. These are delta changes. Okay. So in case, why do we keep these edit logs? Question is that why do we keep these edit logs? So that in case file system crashes, right? If file system crashes or name node crashes, what would happen is the whole memory be will disappear, and at the end of it, the uh, at the end, when the memory disappears, there will be nothing left. But in the case, if you have edit logs, you can recreate the whole situation by applying one edit log at a time on the previous snapshot. Okay, so periodically we take the snapshot of the metadata, put it in the disk, and continuously NameNode keeps on creating edit log. So you have got a snapshot, then we got one edit log, and then another edit log, and so on. So we keep on doing that, and in case system crashes, SDFS can be the metadata could be recreated by uh, say snapshot at yesterday and edit log of today morning, and so on. For every change, this would happen. Now, so in case name node crashes, we can recreate the metadata by combining snapshot with edit logs. All right. Am I clear to everyone? All right. And periodically, we keep on recreating, because this process of appending edit logs to snapshot to recreate the metadata is very time consuming. Therefore, it's more economical to periodically take the snapshot, okay, and to have the complete backup. All right. Do I make sense to you, Ajay? All right. Great. Okay. So I'm hoping that everyone is with me so far. And since there are two classes already over, that's why I've tried to just go through where we stand as of now. Next question from Ravichandran is, when it goes to the file system to get the snapshot only first time? When it goes to the file system to get the okay, snapshot is created by name node periodically. So, okay, periodically. So let's say name node is running today. Periodically, it'll save the snapshot to the disk, and then whenever if name node crashes or we restart the name node, it's going to read from snapshot. All right. A question from Ajay is, can a name node crash after it confirms and before it writes to edit log? After it confirms and before it writes to edit log? No. Okay. Because edit log and confirm, I think once it writes to the edit log, only then it confirms. Okay. This is a very, okay. So I think it writes to the edit log and then no, actually you are right. It could happen. You're right. So yes, this could happen because name node could crash after it has received the confirmation from the user that the file has been written, but it and it updates the metadata, but it is not able to send it to the edit log. Okay. So I think it can, if it crashes, the data might get corrupted. All right. Might get corrupted as in a particular user's change might disappear in this case. Okay. So a question is, Ravichandra's question is, if standby name node is there, then what in that case, the control switches to other node. Okay, actually this needs to confirm. Okay. I'm not sure. In the initial design, the edit log was being done after the confirmation. And in the new design, I think the confirmation was happening after the edit log has been committed. Okay, I need to basically confirm. All right. All right. Great question. Great question. All right. Okay. All right. What was the next question? Um, so Robert's question was mount tables. Mount table was discussed last time, but still not clear. My understanding is mount table is needed when single name node is not enough. That's correct. Yes. And all right. So okay. So the way. All right. Okay. So Ravichandran, was I able to answer your question? In case one name node goes down, the control switches to the other name node, and the since name other name node is keeping itself updated with all the information of the metadata, therefore the other standby name node would have the fresh data, and then the control switches to other one. All right, do I make sense to you? All right. Now let me take you through the mount tables. All right. So how is the mount table generated and get used one more? Okay, so let me just open the same slide. So, okay, so this is our main component. How do you store? This is the traditional way we stored, but there were problems with that. And then we have name node and data nodes. And then we discussed that files are cut into pieces while storing on each data node. And each piece or block has got multiple copies, and these copies are located on other one. Name node is not like this, whereby user will read everything from the name node. Instead, it is more like this, that user is having a driver on which driver who does the basic work, and the driver talks to individual data node for reading the data. Name node is consulted in the beginning. This is another way of looking at the same architecture, and this is anatomy of a write. And okay, so next thing we discussed was the single point of failure with respect to name node, and the metadata and edit logs. Uh, okay, so yeah, next thing, this was another thing which we discussed, that name node has got its own clone called standby, to who both end user, the client driver, name node, and data node keep updating. Standby is updated by everybody, so that standby is always a reflection of name node. Okay, now the next question which we discussed, next topic which we discussed was mount tables. Okay, when do we use mount tables? Sometimes name our folder structure or our file system has become so huge that the metadata of that file system is not fitting into the memory of one name node. Okay, so one name node is not able to handle the memory related to one big file system. Uh, the imagine that your whole organization is using a single file system, and this file system is containing everybody's code, everybody's folders, files, and everything. So this file system, even though it's distributed, but since the whole metadata is kept in the memory is the bottleneck. So in these kind of situations, what HDFS came up with our little traditional approach, whereby we keep a configuration with the client library or client driver. Client driver is given a config file in which it's configured that if there is a request for a particular folder, to which name node does it need to go. So it's happening on the client library side. As in client library, the command like Hadoop FS, or the API, the HDFS API that you use to talk to name node or to talk to the HDFS. So it's happening on the client side. User, which is you, when they when they install the client library, they will also configure the mount tables in their configuration. Sounds like very opposite to the centralized way of doing thing, but if we keep this mount tables in place somewhere central, then that central server is going to be a bottleneck. Therefore, mount tables are kept as separate. The other reason why we used two name node, other than the other than the memory overflow, is when we realize that there are too many read requests or too many write requests are coming to name node. If there are too many requests are coming to name node and name node is not able to cater to those many requests per second, then it's wise to split the traffic by saying that for this folder, let's keep the metadata somewhere else, and for this folder, let's keep the metadata somewhere else. So one is lack of memory, other is the number of network bandwidth. Okay, so those are the two reasons why we keep the federation. This is called federation, meaning multiple name nodes. And All of this information about which folder is on which name node, and folder is of top level directory. This is a mount point. We call them mount point. Okay, the way when you mount a file system on your computer, it gets C colon, D colon, and so on. So you can think of mount table as a list of C colon, D colon, E colon, and each of these C colon, D colon, E colon knows where and which device exactly we need to talk to. Okay, so this way mount tables are kind of your mount tables. Like if you have used Unix, there is something called fstab. Or when you type a mount command, it shows you all the hard disks that are mounted. In the same way, client library contains list of name nodes mapped to individual folders, top level folders. And client library decides that in case we want to access this particular folder, we go to this name node. If we want to access that folder, we go to that name node. Okay, so that's the role of a client library. Did I make sense to you? Question from Patrick is further, if mount table is kept in a different client, can it get out of sync? Yes, it can. So it has to be manually synced. Okay, while installing the client, we need to make sure it does. And every time we change the mount table, we'll have to propagate those changes across all the clients. All right, all right. So okay, so maybe they have made some enhancements to mount tables now, but till the version we have earlier, mount tables are manually synced. There is no kind of central mount table server. All right. Okay. A question from Akshata. How many maximum number of name nodes allowed in federation? The limit I'm not sure of. Okay, I'm not sure about the limit. All right. Although if you look at this HDFS federation, it would look to you that there are basically two different file systems, two different completely islands of file system. But the different part about this HDFS federation is that they use the same data node. Okay, so you don't run the separate data nodes process for each different name node. They actually use the same list of data nodes. Okay, that's the beauty of name nodes. A question from, yeah, that's a very good question. Thank you, Patrick. Yes. So, question from Patrick is, it seems the mount table needs to be updated often because if new files, okay, let me explain again. So, mount table is like this. Mount table is slash, let's say data is goes to, say, name node called a1.cloudxlab.com colon 5030. Okay, slash src or slash proj would go to b1 or say a2 dot cloudxlab.com 5030. I'm just taking a few examples. Now, rest would so rest would go to, okay, so it's for top level folders. Okay, top level folders. Okay, so this is how a mount table would look like. That if the request is going to slash data, the request is redirected to this particular node. If request has come for slash proj, the request is redirected to a2.cloudxlab.com and so on. Okay, so this top level structure does not change quite often. Therefore, this mount table would not need to be updated too often. Do I make sense to you, Patrick? All right. I'm hoping my voice is clear to everyone because some people are complaining. All right. Okay. I think I'm on the right network. Yes. Let's see. Let's see if it breaks again. Then we'll see. Okay. Okay. So I hope it's clear now. Okay. Okay. Now let's go to the next question. So we talked about edit logs. We talked about mount tables. And then now a question was input splitted data will always be 128 MB. The answer is no. It can be configured in the file system. Okay, it can be configured that the default block size is this much. Okay, all right, all right. And you can change this block size as well, even at a later point of time. Okay, so any other questions before we move further? Great, great. All right. So I'm hoping that everybody is with me. All right. So we discussed about how does HDFS work. All right. Samip says there is a breaking of the voice again. All right. All right. Let me just check if things are okay. Any other question before we move forward? Okay. Okay. Anil's question is this we have discussed. Okay. Could you copy paste again, Anil? Okay. A question from Anil. How will Hadoop handle if processing needs to be done on two files that are distributed across two name nodes in federation? Okay, so it'll handle in the same way. So, okay, although we are jumping ahead a bit, okay, but to answer this question, let me try to make it a little simple. Okay, so, uh, okay, so should I answer it or should I try to fix the net first? Okay, looks like the voice is breaking bad. So let me just check. All right, let me switch the internet.
Muted. Muted. Unmuted.
Hi everyone. I hope my network issues are resolved now. All right, let me say a few more things, and then in case it's still breaking, then I'll need to look into it again. Gizzy and Samip, is my voice clear? Is Gizzy and Samip, is my voice clearer now? No? All right. So the question was, if Hadoop has to handle two files that is distributed across two name nodes in federation, then what happens? Okay. So is everybody with me? Is my voice clear and better than previous one? Okay, looks like I'm not getting answers. That means I'm disconnected. Mm-hmm. All right. Yeah, this is all good. Okay, okay. So everybody is able to hear clearly. All right. All right. All right. So, okay. Okay. So the way Hadoop handles processing is by delegating work to many computers. And instead of transferring data and bringing the data to the code is transferred to the data nodes that contain the data, and each section of the data is processed independently and results are derived. Now, we will get into these details in this session. So, even in the federation, the same distribution of the logic is exactly same. So, there is nothing breaks. So, if we have to get done something in the federation, what happens is we find out the data, we find out all the data nodes involved and what are the various execution engines near the data, and we send the work to those execution engines. So this we will discuss now. All right, great. All right, great. So how many of you were able to download file into HDFS? Okay. And how many of you were not? Yes. Yeah. Raul was able to do that. Robert was okay. All right. Samif was able to do. Could not log in. Okay. Actually, there are two people who are still, it shows, waiting for names. Okay. Akshata was able to do on Hue and so on. Great. Great. All right. So basically, you all have to do is one, you go through and try to connect to Ambari and Hue. So in Hue, you can see there are these files, and here in the file browser, and this is the console on which you can type. All right, this keeps logging out. No worries. I will. Okay. All right, I've logged in. So this is the console, and in case I want to log in from my Windows, or if I don't like this browser one, I can use SSH or PuTTY. Okay. So this is my machine called e.cloudxlab, which also has my home folder. Similarly, this HDFS also has my home folder. This is HDFS file browser in the Hue. This is the HDFS, whereby these files, you see, this information about directories and the files is stored in name node, while the actual data, what is inside a particular file, let's say this one, is stored on data node. Okay, so question comes to us that if I have to find out where is my particular file, okay, let's say where is that let's which what's the command there? We are saying, okay, let me try to um okay, let me try to find out where is this file located. Okay, so let me try to do this, and okay, good. So let me try to execute this command to find out where is my file. All right, let's just find out where is my file. Okay. It's a single command, although it's wrapped into two lines. It's a single command. And I can go to my console and say hdfs fsck. Okay. Show me the blocks, show me their location, show me the racks, and show me the individual file. And then we tell that this is the file which we are trying to locate, right? So this file, which pick.udf, is, yeah. So let me try to answer first question. Robert's question is that this file called this file, say pigudf.jar, even though it's available in this folder, you can't see generally in the local one. Okay. Even if it is, do you see anywhere pigudf.jar? Even if I delete it from local, it'll still be there in the browser. Okay. These two file systems are different. This is different. This is HDFS, while this is the file system of this machine called E. This is the file system of E, not the HDFS. So when I say LS, I'm talking to this particular computer called E. I'm not talking to the HDFS. Make sense to you? Okay. All right. Good. Good. So basically, these are two file systems, and the way you can think of them is your laptop, that's one file system. Your laptop might be having one file system, then console, or you can say e.cloudxlab, that's another file system, and third one is HDFS. So from your laptop, you do an SSH, okay, and log into e.cloudxlab, and from there you can use a command called Hadoop fs to talk to HDFS. Make sense to you? You can see this. So if I am this console, ouch. Just give me a second. Let me check what's wrong with the network.
Muted. Unmuted.
Hi everyone. I've switched my network connection. Is it better or worse now? Okay. And I believe, yeah, Tracy and Akshata never faced problems, so it cannot be a problem on my side. Okay. So I've switched to a slower network now. In case this gives problem, I'll switch back to the same network, the previous one. All right. All right. Let's try this now. Okay. Now let me log in here because it'll get disconnected because my network went down. And all right. So here I am. So I was explaining the difference between the file systems. So there is this file system of e.cloudxlab. There is your laptop, and third one is this. From your laptop, if you have to talk to HDFS directly, or from my laptop, if I have to talk to it directly, I will use this interface, Hue. I can just click on upload and upload whatever file I want to do. And then I can also download and do other things here. If I want to upload file in e.cloudxlab, then what do I use? If if I want to upload file, okay, upload, download file, in the same scenario, so if I have to upload, download from E to e.cloudxlab, then what do I use? For this, I use um, SCP. If you are on Windows, you can use a tool called WinSCP. These are remote way of copying files. Okay. I even use another tool called rsync. Rsync is a command to remotely sync two folder structures. So that also I use quite often. So to copy the data from your laptop to e.cloudxlab, you could use, if you're on here, say, let me open my terminal. This is my MacBook. This is my local this computer on which I'm this laptop. So I can use SCP from here, rsync from here. Rsync and SCP are installed by default. So let me just show you again. So I could use rsync. You see, it is the wonderful tool, and SCP is for copying the file. Rsync is synchronizing two folder structures, and SCP is okay. This can only happen between my laptop to e.cloudxlab. Okay. This, when I say ls, I'm showing my home folder located at e.cloudxlab. So similar everywhere, you're given a home folder in every file folder structure, whether it's your laptop, whether it's your logged in e.cloudxlab, or whether you are on Hue. So here my folder's name is user Sandeep Giri. This is a home folder. And on my local, on e.cloudxlab, my folder name is /home/ Sandeep Giri. While in here, my folder name is capital user /Sandeep. PWD means present working directory in Unix. All right. Now question arises, what do you do if you have to copy data from e.cloudxlab to HDFS? So in that case, you use a command called Hadoop FS. Okay. Most of you have already gone through this list of commands. So using Hadoop FS, you can copy data from the local file system, which is e.cloudxlab, to Hue. Okay, by using a command called copy from local. All right. So as I have demonstrated last time, so we were able to copy the file from here using Hadoop FS copy from local. All right. Now other than this, there is a roundabout way. And that roundabout way is first you upload data into Hue. If you want to take your file from here, from your laptop to e.cloudxlab here, in this directory, one way was using SCP or WinSCP or rsync. Those are the tools you might have to install. But there is another way. You upload data into HDFS and then copy to here by using Hadoop, FS, copy from copy to local, and then I can copy my data from here. Let's say I'm going to upload a file into HDFS. Okay, and the download folder is safest, not really. Okay, so all right, let me just upload this 77 MB file. Which one is smaller here? Let me just take this particular file. Android file transfer DMG. I'm uploading this some installer into HDFS. Okay, and then I go to my console. Let me close this terminal because it might create a confusion. I go to my console and there I could say Hadoop FS and let me check it has come or not. I'll say Android. There is no such file. And okay. All right, let me just check if it got uploaded or not. Let me sort the data by date. All right. No, it did not get uploaded. So let me try again. Okay, it's still uploading. All right. So you can see that now if I say here Hadoop fs minus ls android star, you will see that the file has been uploaded in HDFS. So using Hue, we uploaded this file in HDFS. Now we can copy this. We can copy this. Copy this to this particular machine, e.cloudxlab. Now it'll appear here as well. Okay, just that there are too many files in my folder structure. That's why. You can see that? All right. Now one more thing. Now when I said, not this. Okay. When I say this, Hadoop fs minus ls is going to talk to HDFS and it's only going to talk to name node because ls gives you only the metadata and therefore you get this. Okay, and here there is one more detail that's provided to you. This means number of replica. All right, this is the number of replica in the HDFS. Okay, for every file you see it's 3. Now if I want to change the replication factor of a particular file, I could say set replica as 2 and let me see if that happens. Okay, now all right, so there should be, when I do fsck again using the way I did earlier, I should see the I should see only two files. All right, let's take a look. Now here you see that it shows a very interesting thing. See, it shows you a couple of very interesting things. So what we are doing here, we are trying to find out how many blocks are there and where are those blocks located. So for this particular file, how many blocks are created by HDFS and where are those replicas? Now, since it's just 3 MB and default size is 128 MB for, for a block size, therefore, it's going to have only one block. All right. Now it says that it's connected to the name node. You can see that name node is running on 50070 port. And this is the internal IP address. Okay. If you want to find out about this IP address, what do? You go into CloudX Lab and you go into CloudX Lab and click on My Lab. You will be by default logged in into lab, and there here you can see the credentials and IP mappings. Okay, so here we are. What is it that we were seeing there? It shows this IP. What was that local machine? It was 5348. 5348, which is a.cloudxlab. That's our name node, right? That's our name node. So it's talking to the name node a.cloudxlab, and it's providing the login ID, number of blocks located, and everything. It's saying that give me the list of blocks. So this is the API call. You can also make the same call. All right. It says that FSE case started by Sandeep Giri 9034 for this particular path at this particular time, and this file is this big and it has got one block only, and this block has got these many copies. Okay, these many copies, as in replication factor true. That's what we said. One replication factor is stored at this location, meaning on this IP address 172.31.38.183, and what is that? 83.183 f.cloudxlab. That's one copy stored there, and second copy is stored on this machine, which is 5348. 5348 is this. Make sense to you? Good. So basically, these are the local IP addresses. These are not the public IP addresses. Okay, because we do not want these IP addresses to be exposed to the public. Therefore, we have created a LAN between these nodes, and then we have allowed access on few ports on our cluster from outside. All right. Now it shows us that the file system is healthy. Total size is this much, and total number of blocks are these many. And here the default replication factor was 3, but in our case, average block replication is 2. Okay, average block replication means, so it sums up the number of replication of each block, then it divides the total number of blocks. Okay, if certain blocks are under replicated means we are not able to copy them everywhere, then this average will be lower than the replication factor we have set. Now here it shows that there are 4 data nodes available. There is only one rack. We'll talk about rack a little while later. Overall, this file is healthy enough. Now let's say we go a little more insecure and we say, I want 6 as a replication factor. Now, as we had talked earlier, that two replicas cannot be on the same node. So since we have only 4 data nodes, it does not make any sense to have 6 replication factor because it can never copy 2 nodes on one machine. Therefore, it can at most have 4 replication factor. So let's go and check what's the status using HDFS FSCK command. HDFS FSCK gives us the file system information. Here, it would show that although the file is healthy, all the blocks are available, but it would be under replicated. Okay, so it says that the FSCK started by such and such, it's under replicated. You see that? And the block You can see that missing replicas are still 4. Okay, it has still the overall copy as 2. It's going to take some time to copy more. All right, now it has copied to all 4 nodes. You see the average block replication is 4. And here as well, if you see, I've executed the same command again after a while. The data has been copied to more number of nodes. You can see 1, this is 1, 2, 3, and 4. Do you see this? So this command, let me also give this command to everyone. All right. So you can instead of checking my file, you can use on your file. Okay. Although my files are read only for everybody, but still. Makes sense to you? So it's a live example. The point I'm trying to make here is 2 replicas cannot be kept on the same node. All right? All right. Great. There are a few questions to Balvinder. All right. Okay. So other people can also help me answer these questions. That way, first question is what machine HDFS is hosted? Okay, so when we say HDFS, HDFS is not a single machine. There are many machines. The only way we can classify is we can say where is name node hosted, right? Name node is the one who is going to tell us which folders are there, which folders contain what files, and so on, right? So right now, if you see when we call anything, we get a name node, this one, which is our a.cloudxlab. The other way, the other way is the other way to look at it is if you go to either MyLab contains more details than this block. Okay, MyLab contains your MySQL credentials, lab credentials, and more videos we are adding here. And so and the IP mappings. All right. Now you can see that this is Ada Cloud X Lab. The other way of looking at it is, you know how? By going to Ambari. All right. All right. I think I would be able to log in. Good. Okay. Here, Ajay's question also, let me just keep it in the notes so that I can answer. All right. So here, you can see that name node. So name node is here. It shows that name node is on this machine. Okay, and this particular machine is running Kafka, name node, resource manager, zookeeper server, as well as this is something important. Lots of people confuse that we cannot run data node on name node. We can. It doesn't stop you from doing that. Okay, and it's more in most of the cases it's completely okay to run name node and data node unless name node is too heavily loaded. In our case, node is not too heavily loaded. Therefore, we have kept other services as well on this particular node. All right. Then we have Flume, Metrics Monitor, NFS Gateway. We'll talk about all of these services slow as we go forward. All right. It has got 4 core, memory 16 GB, and whatnot. All right. So that's about the first question. Second question is All right. Which machine Hue interacts with? Anybody? So Hue is running on a different machine. Hue is the service. Hue is kind of the client, the web interface. It provides you this web interface. This web interface is running on d.cloudxlab. And this is a Django program. It's a web server running on d.cloudxlab. D is one of the nodes in the cluster. And this d.cloudxlab, which is running Hue, is essentially talking to HDFS the way you will talk using Hadoop FS and all those commands. In the same way, the Hue is talking to the Hadoop. All right. Although this d.cloudxlab is also running Hadoop related services. And where is the d.cloudxlab? Let's take a look at it. What is d.cloudxlab? d.cloudxlab is 4377. Okay, if you go into Ambari and say hosts, in the host you will see 4377. And what all is it running? It's running Zookeeper, Datanode, Flume, NFS Gateway, and all of those default services. All right. Good. Great, great. Next is if we only remote log into e.cloudxlab and upload files from Hue, it should show up in console. No. When you upload files into Hue, you are not uploading files into d.cloudxlab. You're uploading files. This is HDFS. This file browser is essentially, if you keep your cursor here, it shows manage HDFS. This file browser is essentially HDFS file browser. All right. So this is HDFS. A question from Ajay, that where is the config file located for HDFS client on a given Linux machine? Good, very good question. So if you install your Hadoop, okay, let me devote a bit of time on this part because some of you have also asked me the same thing related to installation and other issues. So let me try to answer these questions. So question is that I'll try a little bigger answer in this case, okay? Because it's a broader question and it's an important question to be answered right now. Although we have mentioned it here, if you have to install, you have to do what we have done at CloudX Lab, whereby you want to install all of this, okay? So how would you go about it? Okay, one is a manual way whereby you will copy Hadoop installer on every machine, and then on every machine you will install services, then connect to each other. There's a cleaner way of doing that using this tool called Ambari. We install Ambari on one machine, Ambari server on the first machine, and then on all the nodes. These nodes, in the beginning, these nodes are empty computers running an operating system. So we install the Ambari agent on every node and then ask Ambari server to install things of its choice on all these data nodes. So Ambari has installed all of these services by itself automatically. Okay. Now question arises that when HDFS runs, when name node runs, okay, I'll try to answer this way. Where is config of name node or data node, right? Although we can control the configuration from here, you can click on config. Since we are not admin of this one, therefore all of these things are read only. Although we can modify the all of these properties, like how big the I'll show you. If you go into advanced, here the block size, the default block replication, and there is, okay, let me expand all of these sections of this. Yeah, okay, I'll just try to show you. So all of the configuration, you can see the DFS block size. This is actually 128 MB. If you multiply it by 1024 into 1024, you will into 128, you will get this number. If you divide by 10, basically it's in bytes. Now, so this is configuration, and since we are not admin, we cannot modify. So Ambari lets you modify and configure all the tools. So Ambari is kind of a remote provisioning tool for you. Okay. Ajay's question is Ambari using some kind of Ansible tool or something similar to configure multiple devices? So Ambari is essentially using its own agent, and there's a conversation that's going on between Ambari and its agent, and that's how this configuration is going. So basically, Ambari does a lot of automation for you, but Hadoop actually can be installed without Ambari using step-by-step process. Okay, but that's too tedious and should be avoided as much as possible. Either if you want to go with Cloudera, you should use Cloudera installer. If you are using Hot&Works, then you can use Hot&Works installer. If you don't want anybody's installer, you can just start afresh, but that will be a little too time consuming to configure and reinstall. Okay, but again, the question is still, where is the config? Okay, the config is located in, let me try to show you. Config is located in etc on every machine, etc Hadoop. You see, in the conf folder, etc Hadoop conf on every machine. And this keeps on getting updated via Ambari. Ambari keeps on manipulating these configurations to configure each and every node. Let's say if we want to see the details about HDFS site, we can take a look at, you can use, in case you don't like Vim, you can use this. Okay, it's a read-only file for you. You cannot change it. So you can see that the default values are configured by Ambari for us in this file, and it shows that the data node is on this machine as well, on this local machine, and bandwidth per se, that's okay. And this is the folder where Hadoop is actually telling every data node to store the data in the local directory. This is where the blocks which are split kept. All right. Here there'll be a place where we mentioned the name node somewhere. There should be a name node. Okay. I don't like this editor. I'll use VI. All right. I think it'll be there somewhere. All right. These are the configuration properties to configure everyone. But I would strongly say that don't touch these files. Let Ambari change these files. And this is where all the information is kept. You can see journal node edits are kept in this file, and we will, okay. Let me. Okay. So do you see the name node somewhere? Yeah, you can see DFS dfs.namenode.http address. This is the address which is told to every data node. Okay, so this machine on which our console is running is also a data node, and every data node is configured using this folder called etc hadoop, and there we are not doing it manually. We are letting Ambari manipulate this configuration file to configure individual services. Okay, do I make sense to you? Ravichandran's question is, I do not see the config file in the attached path. So you can see here, if you go to cd/etc, don't look in Hue because Hue is the HDFS. We are talking about individual native file system, because at the end of day, all of this data goes into the local file system. Okay, so this is where Hadoop keeps the blocks. Okay, this is where Hadoop keeps the data block, actual data, which are split into small files. You can see this is something which it keeps on creating for blocks. These are the actual size of files. These are the actual blocks, raw data blocks. This is where every data node is storing. This is where every data node is storing the actual block. Okay, under under the Hadoop HDFS folder. Hadoop HDFS data. Okay, is everybody with me on this so far, or did I confuse you too much? I understand. Okay, okay. So I mean, I might be doing something really, really quickly. I might not realize that I'm flipping through things really fast. So feel free to stop me because I may not realize that I'm faster. One, because over the network there is always a latency. Second, because I'm used to these things, so things look very obvious to me. Therefore, I might overlook many important things. Okay, is it clear whatever we have discussed so far? Great, great. There are a few people who have joined only for this session. Are you guys on comfortable, or it's too much for you? Because I know that you could not attend my first two sessions. Alex, and there was one more person. Yes? Good. It's okay to go at a little slower pace in the beginning because at later point of time, will be everybody will be comfortable. All right, so let's move ahead. Great. Yes. All right. So today, Do you guys need I forgot to ask. Do you guys need a quick refresher of Unix file system, or you're comfortable? Okay. Anybody else need a quick refresher on a file system, Unix file system, and Unix commands? I'll just go through really, really sharp in like 10 minutes. Okay. Okay. All right. All right. Okay. I did not realize that the break time is, I've skipped break time. So let me take a break. Okay. So break for 10 minutes and back back by 10:04. I'm talking in terms of IST. All right. Hi everyone, I'm back. So should we start now? All right. Great set of questions. Keep the questions coming because your question might help other people as well. And okay, okay. Samip's question is there a requirement in downloading a virtual machine? There is no such thing. Um, all right. So you can go ahead and download the virtual machine. All right. Okay. Just a second. So, do you have any other questions? Also, you can see that out of six data nodes, four are down. Okay, and still the file system is working fine because the same data has been copied elsewhere. Okay, it says that uh, no zero corrupted, but these many are under replicated. Those will be recovered. Sorry, my screen was off. Yeah, I was trying to show you that 4 out of 6 data nodes are available, 2 are dead. Still, there are only 3 blocks which are missing, and they'll be, and rest will be recovered. Okay. Had it been some other file system, it could have been very difficult to handle this kind of scenario where two machines are down. All right. Okay. You can download Cloudera, Hadoop, and that'll be okay. We don't have a problem with that, but there's no need as such. Okay, but you can download either the Cloudera or the Hortonworks. It's almost the same thing, except for additional, mm, not so much needed tools. Okay, the core is same. The common denominator of both the things same. All right. All right. Did I answer your question, Samip? Is- All right. Great. So, any other questions before we move forward? So far we have been. Yeah, I was asking a question before the break. This is answered. If we only remote log into this and upload files from Hue, it should show up in the console. No, it should not, because there you are uploading file into HDFS, and console, when you say ls or you roam around the file system, you are talking to the native file system. All right. So before the break I was talking about using do you need a quick refresher on Linux, or should I move ahead? Yes. That's also a good idea. Balvinder says that how about dealing with it when it come across? That's also a good way. So Akash was asking, who else? There was one Akshata was asking, and one more. All right, let me just take you through it. I think it won't take too much time. It'll also make everybody comfortable, and maybe you will get to know something new. Those who have already known this, I should not take too much time. All right, I'll just take you quickly through all of this. So it's going to be a little fast. All right, so in case you have not been in case you are not from a Unix background, you are from say Windows background, this quick refresher should help. In Unix or Linux, everything is a file, be it mouse, keyboard, random number generator, a device which listens to everything, sound card, everything, all of all of these kind of devices, the monitor, the keyboard, the mouse, the headphone, the say USB, say network card, everything is a file. Okay, and all of these are kept organized in the folders inside the folders, and there is a top level directory which is called slash is like top level directory. Okay, or you can say that top level directory is null, under which every file is kept. Okay, you can create directory within a directory, you can put the files inside a directory. Slash proc keeps the information about the processes running on a system, so you can go to cd proc and you can browse around and find the details about each and every process. Okay, process is something which is running currently and is loaded into the memory, and processor is executing the process, various parts of the process. Now, slash etc is generally reserved for the configuration file. This is just convention. Slash tmp or slash var tmp is for temporary data. Okay, and slash home contains the directory for each users. So this is, we are talking about Linux file system. In case of hdfs, the information is kind of similar. Okay, there instead of home is slash users that keeps the home directory for all users. Next is, you can refer a file either relatively, saying from my current folder go up. Go up means dot dot slash into the file and into another folder. So I'm saying here in the first example, I'm saying that go up and then go to Sandeep's directory and then give me XYZ file. Or I can refer a file by absolute path slash tmp. Okay, that's an absolute path of a directory. Files have permissions, you can't change slash data, for example, right? So files have permissions, and you cannot modify some data, you can modify some data. Now, what's a command prompt? It's a place to execute commands. A command, a file, executed a prompt in the following manner. So first there is a command, then the argument. So when I say Hadoop space fs, Hadoop is a command, fs is an argument, minus copy from local is another argument, and so on. Those are the parameters or arguments. All right. So, and the program itself is another file. So again, when you are executing a program, you can either call it by absolute location, or by relative location, or by just the name. In case you do not provide the location of a program is searched in a variable called $path and then executed. Okay, so $path contains column separated directories in which basically tell the console or the shell that when a user is asking to execute a program, these are the directory to search for. Okay, this method, this whole idea of a path is common to almost every operating system like thing, even for virtual machine. When you say, even for JVM, when you try to run a class, it looks for the class in certain folders designated by JVM. Similarly, in case of pig, as we'll study, when we look for something, there is a designated folder structure in which it will look. Similarly, when you give the name of a program without the absolute location or relative location of a program, only the name, in that case, the shell looks for a environment. There is something called environment variables. It looks in the path environment variable, and then it finds out from there where is this program located. Okay, so when I say ls, okay, let me just do a little dissection. When I execute this command ls, this ls is being searched in an environment variable called path. And how do you see environment variable? By saying either set shows all the environment variables defined to you, or a particular environment variable, say echo $path. These are the environment variable. So $path is an environment variable which stores column separate list of folders in which to find a program. So when I say ls here, this shell looks for this environment variable, and then first it will go to this folder and try to see if ls is there or not, then this one, then this one, and then this one. This is where it will find the ls command. So you can see, if I say which ls, okay, it says /bin/ls. So it has found ls command in this. Okay, so this is the way a program is executed. Okay, when I say which Hadoop, when I say which Hadoop, it says the file is located in the bin/Hadoop. So you could say go to bin and say ls minus l. There are so many things. Okay, so we could say, okay, you can see that this Hadoop is a symbolic link. This is a link. This arrow you see, it's not really a file. It's a link to another file. Okay, so in a file system, there are certain files which are links to somewhere else. There are two kinds of links, soft link and hard link. That's something beyond the scope, but here it's basically a soft link. All right, so if you remove Hadoop, if you delete this will not get deleted. It'll remain there. Correct? So this is basically pointing to the Hadoop's actual location. Good. So this is the way, and that's why we don't have to type, because I remember somebody asking me this question, that you are teaching something totally wrong. You are typing Hadoop command instead of saying /bin/Hadoop, and I was amazed at that. And so, okay, so yeah, when you type Hadoop command, it essentially searches the path and finds it automatically in the path environment variable. And this /bin is one of the folders mentioned in the path environment variable. All right, so either saying bin Hadoop, okay, or what is my current folder, let's say this, or saying dot slash means in the current folder execute this file. Okay, and since Hadoop is a symbolic link to somewhere else, it actually represents the same thing. Okay, so when I say cd, it takes me to my home directory. This is my home directory. Or I could say cd and tilde. Tilde is also meaning home directory. Also, my home directory is stored in this environment variable called home. Okay, so cd tilde, or cd $home. All these three things mean a lot. Okay, So, okay, I'll not get into more details because if I go into more details, there are no limits to it. It might take a couple of hours also. But if you want to go into more details and if you have bigger doubts on Linux, you can write to me. I enjoy working on Linux and Unix, and I'm quite comfortable with it. All right. So, so to interact with Hadoop, if you say Hadoop space fs, you talk to HDFS. If you say Hadoop space jar, you talk to MapReduce. Okay. Now, there are commands like cd. Okay. There are commands like cd. To change a directory, you use cd. To create a directory in the local folder, you use mkdir. And mkdir for creating the local folder. And to create a directory in Hadoop HDFS, we say Hadoop fs mkdir. Okay, this is for creating directory there. We have to provide a directory name after this. We have to say Hadoop mkdir my directory. It'll get created in HDFS here. Okay, so if I refresh it, you can see it got created. But locally, it does not get created. You can see it's not created. All right. Now this is a quick idea about HDFS. We will again touch base on few commands such as how does the piping work. Also, to see a file, you can either in case you are not sure about what kind of file is it, you can use a command called file, and then you provide the argument, right? So that way it'll read through the file and figure out what kind of data is it. Okay. Sometimes in Unix, people do not specify the surname or the extension. In those cases, the file command comes pretty handy. And in case you want to see the file, what is there inside file, you can either use cat command. Okay. In case you get stuck in any of the prompt, you can always press Control C. Control C kills the current running program. Okay, don't press Control Z. If you press Control Z, it basically sends the current running program into the background. Okay, to resume, you'll have to press FG. Let's say there is a command called PS, and let's say I am in a file. So to edit a command, we can use another program called Nano. Okay, let me just show you this. So I am in this file. I'm reading. This is the editor. If I want to send it to the background, I can press Ctrl Z. Okay, it's not sending. I think this is dishonoring Ctrl Z. So I can say Vim. This I can press Ctrl Z. It sends it to the background. I can say FG. It comes into foreground. All right. If somebody is logged in from two consoles to into this what do you say into this webinar, if you are having multiple logins, please use one because we have reached our attendee limit of 26. Okay, for the webinar. All right. So this was a quick refresher on the file system. I hope everybody's okay with it. All right. Let's move on. Okay, looks like somebody is trying to join. All right. Kannan, is it clear? Is it a little better with respect to the clarity on Linux? Okay, Kanan, are you with me? All right, no worries. So this was a quick refresher on Linux and went through the HDFS questions and also reviewed whatever we have learned so far. All right, good. Now the next part, let's move to computation engine. Okay, let's move to computation engine and let's try to understand first why we need this kind of computation engine, and then we will go step by step so that all of us are totally comfortable with the idea of a distributed computation engine. All right? All right, so here we go. Question to all of you is, let us say you have a normal computer like your laptop and you attached a terabyte storage to it. If you have 10 billion names, 100 characters each, how much time will it take to order the data? How fast can 1 gigahertz processor sort 1 terabyte data? And 1 terabyte, this data is basically 10 billion names of devices having 100 characters each. Anyone? Nandkumar says that around 50 hours. Okay, interesting, interesting. All right. So the idea here is I want to, because there is nothing wrong in the wrong answer. All right. There's nothing wrong in a wrong answer because almost even if you are wrong by 3 times, still it's okay because it's a very subjective question. Yes. So Nandkumar says 50 hours. Josephine says 6 hours. Around 6 hours. That's Akash. Anybody else? Yes. So even if your computer is extremely fast, it might go up to 10 hours. In the best case scenario, you will be able to do it in 6 hours, but in normal scenario, it could go beyond 10 hours. All right? Now, this 10 hours or say 6 hours is after I have optimized this whole algorithm. Most of us, when we look at this number saying, oh, we are taking 1 terabyte data, sorting 1 terabyte data in 10 hours, there must be something wrong in the algorithm. Specifically, those who have not seen much data before. Okay? And the chances are that most of us who have not experimented on bigger data computing, we believe that the computation takes a very less time. Okay, computation takes a very less time. Also, you did not see the sort as such. You must have seen the situations like you have a existing database table and you want to create an index on that database table. And creating an index in a way, is sorting the data of that column and preparing an index. Okay, whether using a B tree or a binary search tree, or there are many data structures. So why do I talk about the sorting as of now? Is because sorting is probably the principal components in almost every algorithm. Let's take a step back. Let's take a step back and so one is that this is fairly slow, like 10 hours is fairly slow, and you might need bigger data sorting. I'll explain why do we need sorting more, and we might have to sort more often. On 8th September 2011, around 4.5 years ago, Google sorted 10 petabyte of data in around 6.5 hours on 8,000 computers. That was the first time somebody sorted such a huge data in the history, and in such a small time on so many computers. Okay, so to do this kind of work, you require really sophisticated techniques. All right. So as we go into the big data domain, 1 terabyte is a common scenario, and sorting is a very common exercise. Again, why sorting is such a common exercise? How many times, okay, how many times have you sorted the data? Yes. Have you sorted the data in your career so far? Who all have? Everybody? Have you sorted the data? Almost everybody does it. Okay, almost everybody does it. All right, now there are many cases where we see the obvious sorting, but there are many places where there is an intrinsic sorting. Okay, uh, do you think when we look up in a database table and there are indexes on a table, when I say select star from a table where name equals this, right, where name equals Sandeep, do you think I'm using some kind of sorting somewhere? So in this case, in the cases like uh, select star from a table where name equals this, is essentially looking up into the index. An index is prepared by sorting the data. So sorting is relevant when I use select clause. Similarly, when I say group by is of course sorting, because the way grouping happens is we sort the data and then we bring the adjacent same record together. That's group by, right? Grouping of the records on a certain criteria requires sorting underneath. Then sort by, or when we say select star from this, order by such and such, that again is ordering. Similarly, when we join two tables in a database, intrinsically, that's also uses sorting of one form or the another. So the way it happens is when you join two tables and there is no index on the columns on the basis of which you are joining the two tables, it actually sorts the data and then tries to look up in one another. And that way, the whole process of joining two tables become extremely straightforward. So the point I've just proved is that whatever you do in SQL, whether select without any group by, whether lookup, group by, order by, joining, all of these have are impacted by sorting. correct? So sorting is the principal algorithm when it comes to data journey. If you can, and sorting is far more older than what you think. And there are every year there are new algorithms of sorting. There are minor enhancements, but almost everywhere the sorting has hit their upper limit. Okay, so the sorting algorithm cannot go faster beyond a certain point. There are only very small uh, improvements that are happening. And can somebody tell me what kind of and also, when we talk about speed of an algorithm, we generally talk in terms of the order, that if my records are 10, it's taking 1 second. If my records are 20, will it take 2 seconds or will it take 4 seconds? If it takes in the linear fashion, we tell that okay, the order, if it's independent of records, we say that it takes a fixed time, or we say O O1, which is it's a fixed time. It has nothing. The algorithm is independent of number of the time taken by a certain program is independent of number of records it is processing. Okay. Second, when I say on is order of n, meaning this algorithm is linearly becomes slow when the data becomes faster. Meaning, if it takes 1 second to process 10 records, it'll take 2 seconds to process 20 records, and if it takes 1 second for 10 records, it'll take 2 seconds for 20 records, 3 seconds for 30 records. That's linear. If you have on square, it means that if it was taking 1 second to process 10 records or sort 10 records, it'll take 4 seconds to process 20 records and 9 seconds to process 30 records and 25 seconds to process 50 records. So that's on square. All right. Now, most of the algorithms, as long as they are on square, they are tolerable. But when they go beyond O(n) square, then they are not tolerable. That's where the big data becomes complex data. When the order of complexity starts going beyond On or On log n, then the data starts becoming complex and complex computation. For example, if you have to categorize records into a hierarchy of things. The way, the way Darwin tries to classify or categorize the human species into into a kind of classification top down, keeping the siblings very similar to each other and so on. So this is called hierarchical classification, and hierarchical classification is tough. Given say all cars that has been designed so far on the globe, if you have to put them in a classified manner on a hierarchy, saying BMW and Ford are similar, these two cars are similar, and so on, then it's going to take a considerable time. So algorithms such as these classification are far more complex. And these kind of algorithm, even though they are operating on a smaller data, say 10,000 records, they might take years to solve. Okay, so if the problem is really, if your problem can be broken down into sorting, most of the problems can be solved in a very predictable time. But if your problems cannot be broken down into kind of a sorting or in a O(n) square, it takes a long time. Also, for those who are wondering what kind of order we have in sorting, it's n log n, meaning if it takes 1 second to process 10 records, okay, it will take for 100 record, it will take 10 into 2, okay, which is 20 seconds. All right. So around 20 seconds it will take. I'm just taking a gross approximations. All right. So that's a kind of importance is there in case of sorting. Which somebody is trying to join and okay. So Anuj, if you are using only one session, you can exit from another because I think somebody is trying to log in because there are limit of 26. All right, no worries. Now I think it's good. All right, so this is what we have been talking now. All right, so we have established that sorting is an important problem, and sorting is something Hadoop tries to do. Okay, that's the only reason I have been trying to explain sorting. That if you look at Hadoop's processing engine called MapReduce, underneath it's essentially ordering data and grouping data. So Hadoop's MapReduce is basically, you can think of it as a big grand sorting engine, which uses many machines and many machines hard disk reading capacity. Okay, many machines computer and many machines. Okay, great. Now moving ahead. All right. So before we jump into the MapReduce and Yarn, let me first explain to you the MapReduce 1.0. Why I'm talking about MapReduce 1.0? Because it is easier to understand. So Hadoop, when it was first created after HDFS, on the top of HDFS was Google Compute Engine, or you can say that Hadoop MapReduce. Hadoop MapReduce comes from Google paper on Google Compute Engine for MapReduce. Okay, Google MapReduce, there was this massive. Okay, now, so this MapReduce was in version 1.0, and let's stick with this, and then we'll talk about it in the current scenario. All right. So exactly the way the work was divided amongst many data nodes, in the same way, the work was divided amongst data node and there was a name node keeping information of what is where. So master and slaves kind of architecture. In the same way, MapReduce was designed whereby there is one node that's called MapReduce, that was called job tracker, and there were many nodes which were called task trackers. Job tracker does not do anything other than maintaining a register, maintaining which task trackers are awake and which task trackers are dead, which task trackers are busy and which task trackers are free. That is the job of job tracker. Okay, so job tracker does not necessarily run on admin node. So it doesn't necessarily run on the same machine as name node. It just runs on one of the machines. But task trackers are generally run on data nodes. Task trackers are generally run on data nodes. All right. All right. Now let's take a step back and say, so task tracker is essentially a process which is running on same machines as data nodes, and job tracker could run on any other machine, or on the same machine as name node. But it's wise generally to keep job tracker separate. So this was the initial architecture of the MapReduce. Now the only thing this structure of job tracker and task tracker did was take your work and run MapReduce on it. What is MapReduce? MapReduce is composed of maps and reduces. It's a logic program. So it took your program, executed on task trackers, got it done by task trackers, kept a track of which task tracker is up and which one is dead. If somebody is dead, then whatever work was assigned to that particular task trackers, it is given to somebody else. Now, what do you get out of this kind of architecture? You got two things. One, you divided your work amongst many processors. You got many processors to solve your problem. Second, second, you utilized you utilized the disk read speed of so many computers in parallel because you are going to send the work, or job tracker is only going to send to those machines which contains the data which we are processing. Okay, say we so in case of MapReduce also, before we submit the job, we tell the MapReduce that, hey, this is my input data, and that input data is job tracker would talk to name node, find out where is that input data located, and then send and then find out what are those task trackers located near data nodes, and this job tracker essentially executes the work on those data nodes. All right, those data nodes. All right, so here this was the first architecture. In the other way, you could look at it this way: that client talks to job tracker keep work assigns the work to task tracker, and task tracker execute many tasks in parallel and then give you back the results. So this was the classic architecture. If you go to any job shop, if you go to any shop, this is what you will get, right? There'll be a supervisor. You'll ask him that this is the work that needs to be done. It'll send the work to the different work persons, and they will do the work and give you the result. This is the classic architecture. Now this is a little detailed. Don't worry if you don't get the MapReduce right now, but we will go into more details about MapReduce in the upcoming slides. User copies the input files into HDFS. That's the first thing he does, because any data you process using MapReduce, so still we are talking about the old one, so don't worry, we're going to talk about new one very soon. So user, if let's say I ask you that here is the file, order this data by the name of the people, and this file is say 10 terabyte in size. So the first thing you're going to do is you gather all the files that make up this data, copy all those files into HDFS, and if you have 10 terabytes, the chances are it's already in HDFS. And then you write your logic in the form of MapReduce, which will order this data by say name, and then you create the jar, you create the code, you create say logic, or prepare a job, submit using Hadoop client. Here client means Hadoop FS, okay, Hadoop jar. So there was another argument on Hadoop command called jar. That's what executes the MapReduce. So user talks to the Hadoop client, that's a command line, that here is my code, and then at that time when user submits the job to the job tracker, okay, at that time of the process, what happens is this job tracker or the client, the MapReduce logic, tries to find out what are those machines that contain the blocks of my data. As we discussed, in HDFS, data is going to be distributed and each data is going to be in the blocks. So accordingly, it finds out what are those blocks and then submits the job to job tracker. Now job tracker would start executing the work. It starts executing the work and assigning sections of the data to individual task trackers and then maintain a job queue. Okay, it's like a worksheet which supervisor maintains that this person was assigned this job and at this time and he took this much time to finish it and so on. So job queue maintains that uh, status of each map and reduce. Okay, and afterwards, once the work is done, once it's finished, it's sent back to the user. In the meantime, in case a particular task tracker did not send the heartbeat for some time, job tracker will ignore the results of that particular task tracker and give the work to somebody else. So this was Hadoop 1.0. Okay, so job tracker took care of maintaining the records of which task tracker is doing what and how much busy is it. And the only language or only computation way that was there in Hadoop earlier was map and reduces. Okay, but luckily, luckily, uh, luckily, when people at I mean Arun, there was one person called Arun Murthy from Hortonworks, and there were few more people. They realized that if Hadoop only did map reduces, it's like saying that in Excel you can only sort in a certain manner, or in this computer you can only use this kind of program. In the similar way, in Hadoop, the only way to process data distributedly was in the form of MapReduce. All right. So no matter what you want, no matter even if you don't want, if you want complex things like, say, you want to run a process continuously on all the nodes and keep on processing data forever, you can't do that in MapReduce 1.0. Similar, there were many more use cases. They were not catered because the operating system and the computational engine were in the same uh, component. So MapReduce did both the things. One, delegating work of job tracker task trackers. Okay, this whole phenomena of job tracker task tracker, that's one part, and the other part is execution or conversion of your MapReduce logic. So both the things were a single unit in Hadoop 1.0. Luckily, in Hadoop 2.0, the two parts, one which is taking care of execution irrespective of what they have to execute, whether it's in the form of MapReduce or it's some binary or anything, right? So separation of that thing, like compute engine and the operating system, was a biggest change in the history of Hadoop. Okay, and that's where Hadoop 2.0 came into play. Nobody as of today uses Hadoop 1.0, and in case you are still using Hadoop 1.0, you should immediately upgrade. It's no longer supported. In Hadoop 2.0, MapReduce, some part of the MapReduce were extracted out. Those parts which were related to resource management. And what do we mean by resource? Which computer is busy, which computer is free, which computer is near to what data, and which computer can process faster and which computer can do the slower. So monolithic MapReduce was cut into two parts. MapReduce logic side, the computation side, and the yarn, which is pure resource manager. You ask it to run a database, it'll run the database. If you ask it to run anything, it'll run it. Or if you ask yarn to do things like give me the status of all the nodes which are free for last 2 hours, so all of this work of resource organization was extracted out into yarn and made very robust. And thanks to this yarn, that today we have competition to map reduce. We have Spark, we have many other kind of processing engine on top of Hadoop. And that made Hadoop very popular and acceptable across the industry. Okay, so this is what this one big change of breaking down MapReduce into yarn was something that happened in the history of yarn, in the history of Hadoop. So yarn means yet another resource negotiator. Okay, it basically talks to various nodes, negotiates with them that can you give me this much resource, and then allocates that resource. Now what it does inside is nothing, not a concern of yarn. Okay, all yarn does is make sure that the application does not cross its boundaries. Okay, just the way an operating system does not care about what logic you have written inside. Like on DOS you can play a game, you can play anything. In the same way, yarn makes it possible to execute any program in the network. Okay, and thanks to yarn, now other than the traditional MapReduce, you have Tez. Tez is basically a faster computation engine for SQL like queries. Okay, so sometimes the computation you can't code, so you write the computation in the form of SQL, and that's what Hive is. So Hive also gets converted into MapReduce, and one of the innovations that happened afterwards were new competitors started coming for MapReduce for various as esoteric use cases. There were new computation engine or computational paradigms started coming into picture. Tez was one of them, and HBase actually started running on Yarn because HBase also runs parallelly on many machines. Next came Apache Storm, and then you have in-memory systems like Spark and others. So as of today, because of Yarn, because of splitting, decoupling the computation engine and resource management engine, which does not care about whether it's a computation or it's something else, it basically makes it possible to delegate, right? So it's like privatization of the work. Earlier, government used to do everything, and then the model of privatization came into play, whereby government ensures the resource allocation, while what happens inside Google or what happens inside a private company is not a concern of the government, as long as it does not cross the boundaries provided by a constitution. Similarly, here also, what individual node runs inside it, it's not a concern whether it's running MapReduce or running HBase. It doesn't care. Yarn doesn't care. Yarn is more like resource provider and making sure that individual application does not cross boundaries. All right. Is everybody clear about yarn? Ajay, your question got answered? All right. Let's talk a little bit more like politics, and that'll clear things. Ouch, we have hit 11 p.m. Never mind. So we will go into the little bit politics, as in this actually is the architecture of yarn is very much like a country's politics. Okay, so we'll go into this ecosystem and we'll take the example of a president or a prime minister of a country to understand how does yarn works. This is important because most of the applications which are written in today's world in a distributed fashion, they are written on top of yarn. So it's very important to understand that yarn provides the ecosystem for various computations. So, So, all right. So we'll go into more details about yarn, and then we'll try to understand what is what in case of yarn. All right. So this is something which we have added couple of sessions back because this was not there earlier. But when people asked for it, we have added. All right. So we'll go into more details about yarn, and then we will go into understanding MapReduce and how to create MapReduce logic. All right. Okay. So if you feel that there are certain things I'm skipping, please feel free to drop me an email at reaches@nobigdata, and we will try to rectify those. All right. And there are some one-on-one pending on my side. I'll respond to those on Monday because Saturday, Sundays are very busy for me. And I'll try to schedule from Monday to Saturday, between Monday and Saturday. All right. So if you want a one-on-one, I'll prefer that you keep it between Monday to Saturday and give me 2 to 3 time slots so that I can schedule the one-on-one. All right. So all of you, please go through the assignments. It's very important. Some of you have done marvelous work. I have gone through the submissions. I mean, the quiz submissions. You can take quiz as many as times as you want. Second, you should basically go through the notes. Okay. Go through the Hue hands-on session and presentation. All right. And there was one more thing here. Yeah, regular expressions. I think I've kept yeah, on the third session you can take a Linux command cheat sheet. All right, Kanan. If you have any doubt about any Linux command, just drop me an email. Either me or my team member will respond. And a whole of my team is actually working on the Hadoop, so they'll be able to answer your questions. All right. Yes, these recordings are available online as well. The by default when you go through the CloudX lab, actually the previous recordings are also available here. Okay, previous sessions recordings. All right. Bye bye. Have a good day. See you tomorrow. All right. Okay. Thank you, Akash. Thank you, Ajay. Thank you, Akshata. Thank you, Anil. Thank you, Ankit. Thank you, Anuj. Thank you, Balvinder, Josephine, Kanan, Nandkumar, Novang, Patrick, Raul, Ravichandran, Ravindra, Robert, Samip, Shubham, Siddharth, and Tracy. Bye bye. Have a good day. See you tomorrow at the same time. All right.